This session will be about leveraging iTwins for real-time insights into water distribution systems. My name is Eugene Lymar. I am a manager of software development here at Bentley Systems. And joining me will be Pratti, the Chief Operating Officer of Digital Waterworks. So first, Ram is going to introduce what it means for a water utility to go digital.
Thank you, Eugene, for the introduction. And hello, everybody. Digital Waterworks is a Bentley company established to help water utilities leverage digital twins to optimize their operations and maintenance. Let's understand the top challenges faced by water industry. According to American Waterworks 2020 State of the Industry report, the top three challenges that water industry are facing continues to be the same for the last 5 years, which are renewal and replacement of aging water and wastewater infrastructure, which is estimated to be about $1 trillion for the next 25 years. And financing these capital improvements in water and wastewater is the next challenge. And the investment gap, or the funding gap needed to do these renewals and replacements, is estimated about $85 billion a year. And finally, the long-term water supply availability is a constant challenge. So the water utilities are going digital to improve their outcomes of delivering safe, reliable, and efficient service to their users while optimizing their operations and outcomes. So the number one challenge they face in meeting this, their needs is data integration. They have mountains of disparate data from SCADA, GIS, billing, metering, all sorts of, with data sources and sensors and whatnot. And then a lot of the data is dark data, which is difficult to access. So it makes the life really hard to accomplish this. Second challenge is just the system complexity. In the real world, everything is interconnected. Name it: pipes, tanks, pumps, valves, meters, SCADA, and then there are weather events, major events, demands, maintenance. All these things, need to be considered by engineers and operators before they make their decisions. At the same time, they have invested in all these various systems. So they want to have a digital twin that would enable interoperability across their enterprise technologies, whether they are engineering technologies, such as what includes hydraulic modeling, asset modeling, information technologies like GIS, operational technologies like SCADA, ERP systems, for customer billing, again, another IT systems, and several other systems. So a digital twin would enable the interoperability across enterprise technologies. So in summary, I would say the digital twin benefits are across the life cycle of an asset, whether it is from capital planning and improvement through operations and maintenance, and during to improve the resilience and response during catastrophic events, to identify vulnerabilities. There are unlimited use cases for the digital twin, applying digital twins for a water utility. So I'll now hand over to Eugene to show how his team built a technical solution to these real-world business challenges faced by Waterworks. Thank you, everybody.
Thank you, Ram, for that introduction. So now I want to jump into some of the goals we had as developers of Watersight when we were starting on this journey. So one of our primary goals was to have quick time to market. So the reasoning here is that we wanted to get a product in front of our users as quickly as possible. We believe that the faster we can get user engagement and feedback on our product, the sooner we can get into a virtuous cycle of build, measure, learn, where we could learn our users' behavior, understand their needs better, and then shape our product to better fit their needs. The other thing we had to do was to leverage legacy. When we were building Watersight, we actually had at our disposal two very rich code bases coming from two separate groups that came together in the last few years. And we needed to reuse the functionality and the domain expertise that has built up over 20 years in both of these code bases. Not only did we want to reuse some of the functionality in the core classes, we also wanted to reuse some of the data models that we had developed in the past. Of course, data security is a very important consideration when you're dealing with infrastructure data. So for us to build this cloud product, we needed to make sure we were following all the best practices to keep the user's data safe. We needed to know that we had control over authorization, authentication within the application, as well as role-based access controls. Now, as any business grows and as any product gains more traction, there will be more users. And what we wanted to do was to architect the system in such a way that it would be inherently scalable. What I was really looking for was a scale agnostic system where it didn't matter if we had one users of 100 or 100, where things would just work in either situation. We needed to build a system that was elastic and able to support the product and more users as the product grew. And of course, of utmost importance is reliability. We know that some of the technology that we build is going to be mission critical for our users, and so we wanted to maintain very high reliability and high uptime. So with these goals in mind, we set off to build our product, which is Watersight. And before I dive into the details of how we built this, we came about this idea that really we were dealing with two kinds of data. The first kind of data was more static data. So you can think of this as the water network itself. So things like the pipes, the pumps within the network, their location, the geometry, all of that stuff would be fairly static compared to some other kind of data that we can get. So things like sensor readings, perhaps hydraulic model results, maybe time series insights into the latest sensor details, and perhaps the results of running machine learning models on the day's sensor data. This kind of data was much more dynamic. And so what we decided to do was really to have two separate concerns, one for the more static data and one for the more dynamic data. So what we decided to do was to use the iModel backend to support the more static data that we had. Now, this isn't to say that the data never changes, and this is not true. If you imagine a water network, there might be pieces of that network that have to be replaced. Or for example, maybe there's some real estate development, some new community that's being built, and so additional parts have to be added onto the network. So the network does change. It's just not as quickly as, for example, a signal that might be coming in every 2 minutes or every 5 minutes. So we decided that the iModel backend would be a good use case for this, because what it allows us to do is to capture the versioning information, so the different stages of that network as it evolved over time. And that being baked into the iModel ecosystem made it very, very appealing to us. We wanted to be able to preserve that kind of history. Besides this, iModel also gave us some very powerful visualization technology. Now, we might not be using the latest and greatest virtual reality and 3D kind of technologies here, but for us to accurately and efficiently represent network data in a geolocated way with map backgrounds and with additional animations and illustrations on top of that, we decided to use the iModel for that, and it gave us out of the box some very powerful capabilities with the possibility to then develop kind of more cutting edge visualization needs in the future as well. Of course, we wanted to bridge some of our legacy data as part of that preservation and leveraging of our legacy. We wanted to take some of our older data formats and be able to still use those within this new cloud context. So with iModel, we were able to bridge that data into iModel and still keep some of that same logic for dealing with network entities within our code. And of course, one of the greatest benefits for me for using the iModel backend was that there was almost no infrastructure concerns for us. What we were able to do was to kind of abstract away how that information is persisted and on what hardware, and we were simply able to use it for its services. And that kind of abstraction becomes very powerful when you're trying to innovate and build new technologies. So with that being said, for the more static data, we also needed a place to put our more dynamic data and a place to run our kind of compute intensive parts of our application. So for this, we actually built our own bespoke Watersight backend. And this was a set of APIs and a set of computational primitives that allowed us to run computations in the cloud to store more dynamic data, things like real-time signals, and then to feed that back into our front end. And the way we tied that all together was by using React. We actually started from one of the samples that the iModel team provides, the sample viewer application, and that was kind of the starting place for Watersight. And we built a lot of very interesting and useful functionality from those humble beginnings, just purely based on the way React works and how React allows you to build these components and share these components throughout the UI and to connect these sort of two disparate worlds. And it was a really powerful technological choice for us to have gone with this, and definitely helped us get to market much faster. Now, I'd like to talk a little bit more about our Watersight backend and how we designed and architected this component. So what we decided to do for our more dynamic backends, so we call this either the action server or the Watersight backend, this part is built on Azure Service Fabric. And Azure Service Fabric, as Microsoft would say, is a distributed systems platform that makes it easy to package, deploy, and manage scalable and reliable microservices and containers. So the idea here is we wanted to build out several services which would support our main objectives and to run those on some cloud infrastructure. So this is very similar to Kubernetes if you've heard of that or have used that in the past. And although Kubernetes, I think, has now surpassed Service Fabric in popularity, we decided to go with Service Fabric for an important reason. And again, that was time to market and to leverage some of our legacy technology. We already had a pretty refined piece of software which performed a lot of the features that we were trying to build into Watersight. The issue there, of course, was that because it was legacy code, it relied on some libraries that were older, so older .NET framework versions and some C++ and some Windows dependencies. And because of that, there was no quick way for us to kind of move into the Linux world that Kubernetes offered. And at the time, Windows containers were still early in their development stage and were not a feasible option for us. That being said, this critical decision to go with a platform as a service versus infrastructure as a service was an important one and really helped us get to market much faster. The reason here being that we didn't really need to worry about managing our infrastructure. Instead, what we did is we had the infrastructure be taken care of by our release services team, and it was basically infrastructure as code. What they were able to do is to set up all the hardware and just have configuration files that would go and through Azure deploy all of the required resources, and then we could just deploy our software on top of that. By having this kind of quick way to stand up environments, whether it be development, QA, or production environments, this really allowed us to move quickly and to push code quickly into our system. And so what we're able to do today because of this is to potentially deploy several times a day versus having much slower loop there. Two key workflows I want to point out for when we're working on building a digital twin. So we rely on what we call our WaterGems data set, and this is a data format that is used in our desktop application. So it's been around for over a decade, and we've had users building out networks in this format. And so what we can do is we can take this data set, and through the UI, we can upload it into our backend, and then that runs a bridge and actually takes that information and sends it up as a change set into the iModel. So we capture changes to that model over time. Now we can also use this data set as the configuration seed to another component we have, which is the on-premise data publisher. The data publisher can use this configuration to then capture data from the on-premise, could be a SCADA system, could be a data historian, and it can push those signals up to our back end, where we then store them in Influx and run them through different data cleaning and machine learning algorithms. And both of these workflows are critical for our users to get their water network into the system and then to be able to push more data as the system runs. There are other kinds of data we can push as well. So we're working on building a bridge that can take just straight GIS data, and we can also upload things like different configurations, as well as information about customers and customer billing data. So now I want to kind of jump back to the front end, and I want to talk about how everything gets tied together on the front end. How do we bring about this more static and this more dynamic data into a way that's useful for the user? Well, we actually rely on some of the iModel.js features that are provided out of the box. One thing that we do is we use feature overrides. And feature overrides are this powerful technique where you can, before rendering an element, change the way it's going to be displayed. So for example, you can change colors, you can change sizes. And what we do is we like to color code information based on some kind of legend. So what you're seeing here is as this time slider moves, we're looking at, it could be either real-time data about the system, or it could be predicted, forecasted states of the system as time goes by. And these colors can represent things like pressures within the system, or perhaps flows within the system. And this allows the water network operator to very quickly get a lot of information about how the system is operating. So feature overrides have been very important for us to be able to render some of this information. We can very quickly see what's on the screen as far as iModel elements. We can then take those iModel element IDs and then go to our backend and then query the latest data for that, and then bring that back and map that into a color and apply this feature override on the fly to show these kinds of colors. Another very useful thing for us has been markers. So as you see this time slider move, you see that the level in this tank shown up in the middle of the screen there changes, as well as the color there. So by having markers, and these markers are basically a way to draw kind of arbitrary information directly into the iModel viewport, by having these, we have a lot of flexibility into what we display to the user. And of course, it can be located correctly in the in the coordinate system that's being displayed in. So a few options for using markers that we've tried. One is you can just display static images. And one thing we did is we had a fixed collection of images for tanks. So we had tanks rendered at 10%, 20%, 30%, up to 100% full. And then we just keep those images cached in the front end. And then based on the value that's coming in, we would pick the one that's the best match and then draw that one live using the marker. If you want more control than just that, there's also a way to render SVGs. So SVGs can be rendered dynamically and can give you much greater control over what's shown on the screen at any given time. So you can actually draw, 100 different tank levels, for example. Another possibility is you can actually go back to your server and ask for an image to be generated, right? And this could be something that incorporates even more data from your backend and more insights, and then you just request those on demand and then render those onto the screen. Finally, with markers, you also have the ability to basically put arbitrary HTML inside those markers. So one thing that a colleague of mine, Mike, recommended was we can even display things like video. So if you have a video tag in HTML5, you can put that into a marker. You could potentially capture things like CCTV footage and just place that directly into your viewport. So a lot of different things you can do with markers. One thing we also did was we took shape files and we made markers that were based on the geometry of those shape files. And then we used those as kind of like buttons to click on different zones within our water networks. So another very powerful technique for very friendly user interface. So if you'd like to learn more about feature overrides and markers, my colleague Mike Belusov has written a great blog post. The link is up here. And this will teach you how to use some of these techniques within your iTwin applications. So briefly, I just want to summarize some of the goals we had and how we achieved those with Watersight by using iModel and our backend. We were able to get to market quickly because we were able to leverage the visualization technique, the versioning technology, as well as the already built out infrastructure of iModel. And just by building a bridge and getting the data in there, we quickly got to move on our prototypes and to evolve that into a product. Also, by picking a platform as a service instead of infrastructure as a service offering, we were able to abstract away the infrastructure information, really just think about the software components of our backend. This was very powerful for us. We were effectively able to leverage legacy. We bridged our legacy data formats into the new iModel world, and we were then able to reuse a lot of the logic that we had in our own backends to work with the same domain elements that they worked with before. What we did is we took that legacy, we started to break that into microservices, and we're trying to make that a more modern and scalable solution as we go. Of course, data security was very important for us. So by relying on authentication and authorization primitives within iTwin, and then by building that in using ASP.NET in our backend, we were able to secure that data and to make sure only people that should have access to that data actually have access to it. Of course, we run things in the Azure Data Center, which is which spends a lot of money and a lot of effort to make sure that they have the most secure data centers they possibly can. And so I feel the cloud is safer in a lot of cases than storing data on premise. So all around a good move there. And then by taking best practices from other engineers and by building a system that can scale horizontally, by having multiple instances of our services run, and by being able to add more nodes to our cluster, we were able to build our own backend to be scalable. Now, iModel was intrinsically built this way. By having those orchestrators which can create backends for you, we were able to plug into that stuff and never really worry about scale. Things just kind of work, and that's really, really nice when you don't have to think about certain concerns and can focus on your own domain. And finally, reliability. By having multiple instances of services, by relying on these distributed systems, we have a system with low downtime. And this is very important, very critical for our customers. So I hope this was useful for you. It was a pleasure to speak with all of you. Special thanks to Mike Belusov and Stefan Breuer for helping me prepare some of this presentation. If you guys need to reach me, my email is here. All right, thank you guys for your time, and I look forward to answering any questions you might have.